Hello, everybody. We are embarking on Chapter 7, Eigenvalues and Eigenvectors. The word eigen is a German word. I believe it means iron or proper. Oh, proper. I'll explain why I think that I'll explain why I believe that word is used. But meanwhile, let's see what these guys are first of all before we even start. So the So first of all, when we talk about eigenvalues, for some reason we use the Greek letter lambda. That's commonly used. So just be aware we're going to use lambda a lot. And so here's the famous eigenvalue problem. And it says like this: if A is an n by n matrix, actually I'm gonna highlight it actually. If if A is an n by n matrix, or when A is an n by n matrix, do non-zero vectors x in Rn exist such that Ax is a scalar multiple of x. In other words, I have a matrix and I want to multiply the matrix by a vector, and that's due by regular multiplication. And the result of that should be a scalar multiple of that original vector. You see, usually when you multiply a matrix times a vector, you get another vector. And that other vector is often, pointed in a different direction, let's put it that way, which means it's not a scalar multiple. We want to know, is it possible to multiply a matrix times a vector, and the result will be a vector that's pointing in the same direction? Because that's what a scalar multiple is. A scalar multiple of a vector is just another vector that's pointing in the same direction. So that's really what we want to figure out. Now, let's just see the words here now. So A is the given matrix. We're starting matrix A. X would be the eigenvector, meaning that would be the vector which makes this possible. And lambda here would be the eigenvalue, because we said we want the product of the matrix and the vector to be a scalar multiple of the vector. Well, what scalar are we talking about? Any scalar? Well, the scalar that we're talking about, we're going to call lambda. And we're going to see that, there's only so many lambdas per matrix, but we'll get to that. That's really what we're going to be working on: solving lambdas, solving x's, finding all these things. So eigenvalues and eigenvectors have a lot of important applications. Blah 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 blah. So here we go. Let's. In general, if lambda is an eigenvalue of the matrix and x is an eigenvector, which corresponds to lambda, for which all the stuff works, then the multiplication of x by the matrix A produces a vector lambda x that is parallel to x. And that is very, very important. That is really, again, geometrically, that's what we're talking about here. And let me just put this all. There you go. Let's just highlight that, and we're good. Alrighty. So here's x. Here's lambda x. So I'm getting, again, it's a vector in the same direction. Here's my x over here. Here, obviously, I have a negative. Lambda obviously is negative. That's why it goes in the precise opposite direction, the polar opposite direction. So that's what we're talking about. But we're saying, but just be clear, A is given. Given an A, we want to find an x and a lambda where this could all work. So just to be clear about that, the A is given. Anyway, let's look at some definitions here. If A is so now with all this talking that we're doing, let's actually get the official formal definition. Let A be an n by n matrix. The scalar lambda. So A is given. That's very important. A is the given matrix. We're not messing around with A. We're not trying to find A. A is given to us. That's what's given. Now, the scalar lambda is called an eigenvalue of A when there is a non-zero vector x, has to be non-zero, such that AX equals lambda x, meaning the matrix A times the vector x produces a new vector, which is in the same direction or parallel, if you will, to the original vector. That vector x is called an eigenvector of A corresponding to lambda, which could, in other words, why are we saying corresponding to lambda? Well, because maybe there's a scalar 3, which will work if I use the vector 9, 7, and there's a different scalar -17, which will work if I use the vector 4, 2, or something. I'm just saying that this is the this is what we. It's possible. It's possible. Now, how is it going to be? Is it not going to be? How do we find these guys? That we're going to get to. That's exactly the skills that we're going to learn in this new section, this brave new section. But for now, we're just getting the the definition straight. So an eigenvector cannot be zero because if it was zero, then the whole thing would be dumb. Because if the eigenvector was zero, then I would just let lambda be zero, and then there'd be nothing to talk about. So a times zero equals lambda times zero. I'm sorry, a times zero equals lambda times zero. Yeah, 0 equals 0. Nothing to talk about. Now it's possible to have a non-zero x vector, but have an eigenvalue of 0. That's possible, but we're not talking about a 0 vector. Okay, that's clear. I'm being very slow and very precise about the terms because it's important we have our terms and terminology straight, and then we can start building, and we're going to start building and picking up. Here's an interesting comment. We're only dealing with real valued eigenvalues in this chapter. Although in theory you can have complex, but we're just doing for this chapter. We're just doing real, keeping it real, as they say somewhere. A matrix can have more than one eigenvalue, as demonstrated in examples 1 and 2. So here's a matrix A. A is given to us, so it's 2, 0, 0, -1. So we want to show that if x1 is the vector 1, 0, right? That will correspond and that will work with the eigenvalue 2. Then we want to show that if x2 is the vector 0, 1, that's going to work with the eigenvalue of -1. So let's do one at a time. So we're choosing x1, which is so A is 2, 0, 0, -1. That's fixed. X1 is our vector right here, this column vector, 1, 0. Now, when I do the multiplication, I get 2 and 0. Well, 2, 0, if I factor out a 2, is equal to 2 times 1, 0. So we see that this was my original vector x. That's still my vector x, 1, 0. And that 2 is the eigenvalue. So x1, if my vector is 1, 0, that is an eigenvector of A corresponding to the eigenvalue lambda equals 2, or x1 and lambda 1. Now let's check out x2 with lambda 2. So if we have, I just lost my, that was a bad move. Let's see, this thing is almost, oh boy, this is what happens. That's the way it is with computers. They make one little thing, and before you know it, you're in a different planet. Okay, here we go. And now that was x1 and lambda 1. Let's try x2 and lambda 2. So again, our A, that's fixed. It's 2, 0, 0, -1. We're not messing with the A. We're given the A, we're not messing with it. We're looking at the vector x2, which is x sub 2, which is 0, 1. Now, if we do this multiplication, here we get a negative, we get a 0 on top, and we get a negative 1 on the bottom. But that's equal to negative 1. I can factor out, a negative 1. I can pull out a negative 1 times 0, 1, my original x sub 2 vector, x2 vector. So we see that I took the matrix A times the vector x, and I wound up getting a scalar lambda, which is negative 1, times that original vector x, 0, which was 0, 1. So we see here, this would be an example of an eigenvector, and by the way, the vector 2 times 1, 0, that goes in the same direction as the original vector, just twice as long. And this one goes in the precise opposite. This is the same length, but it just goes in the precise opposite direction if you were to graph these. Okay, let's look at another example. So now we want to verify eigenvalues and eigenvectors. So for the matrix A is equal to, now I have a 3 by 3 matrix. Notice that we're always dealing now with square matrices. A is 1, negative 2, 1, 0, 0, 0, 0, 1, 1. Okay. Now a lot of you brilliant people will recognize right away that A is not a invertible matrix, but no one ever said that A had to be. In this example, A was an invertible matrix, but again, no one's discussing that. At least at this point, no one's saying anything about A being invertible. So we want to now how do you find these x1, x2? That's what we're going to be learning. But for now, we just want to give you the answers and just verify that they actually work. That's all we want to do, is just very simple, just go through, see that it works. So x1 is this vector here, negative 3, negative 1, 1. x2 is 1, 0, 0. And these, we want to verify that these are eigenvectors, and we want to find the eigenvalues. Finding the eigenvalues, if you know the eigenvectors, is very simple, because you just do the multiplication and just see what the scalar is. But let's just do it. So when we take this 3 by 3 matrix, when we multiply it by the first vector, negative 3, 1, 1, well, look at that. We got 0, 0, and 0. Yeah, because that's negative 3, positive 2, positive 1. Yep. And we get 0, 0, 0. Very simple, very, very easy, very simple. Wow. Now, 0, 0. Now, we said something, you can't have a 0 vector. You could wind up with a 0 vector. You just can't start out with a 0 vector. But I could factor out the 0, so to speak. And I get 0 times my original vector, negative 3, negative 1, positive 1. Now, of course, I could have put any vector in here because I'm multiplying it by 0, but it is 0 times, technically it is 0 times that original vector. I could put in the original vector, it's 0 times the original vector. So 0 is the eigenvalue, negative 3, negative 1, positive 1 is the eigenvector that correspond to the original matrix A, 1, negative 2, 1, 0, 0, 0, 0, 1, 1. Okay, so that's how that works. Now let's try the other one. So So now we're going to do we're going to take the matrix A, we're going to multiply it by our second vector, which is just 1, 0, 0, and there we go. And when we do that, lo and behold, we get 1, 0, 0. Right, the bottom two guys just zero out, and here I have the 1 and everything else zeroes out. And now, very simple, very easy to multiply. Thanks for that. And this actually is my vector, my original vector x, or x sub 2, and so I'm just sort of pulling out a 1, so to speak. So my eigenvector is 1, 0, 0, and the corresponding eigenvalue is 1. So x2 is the eigenvector corresponding to the eigenvalue, lambda 2 equals 1, and that is the way that goes. Okay, that's all I want to do for this particular one. I want this first one to be very simple. I want it very, very simple, just to give you the definitions and show you how this stuff plays out, and we'll get to the good stuff next video. So I'm gonna stop the recording. Boing.